So, welcome to another Phi Guy Francois video. Today we're going to be talking about the two-part linear motion problem. Yes, that's right, the sequel is back. So, now let's jump right into it. What does a two-part problem entail? Well, it's really only one thing. Two-part problem entails a change in the acceleration. So if you remember from the first video, our equations only work so long as the acceleration stays the same. If the acceleration changes, then our equations fall apart. So that's why we have to separate them out into two parts. Well, what do I mean by that? Well, let's take a look at an example problem. So for an example problem, we got a car accelerates from rest at a rate of 2 meters per second squared for 10 seconds, after which it slows at a rate of 1 meter per second squared, negative, until it stops. How far does the car move in total? So as you can see, our data table is now a little bit different than it was before. Our data table is now involves part 1 and part 2. So we can separate these things into two separate sections. The first section would be when you have one acceleration. The second section would be when you have a different acceleration. So in this one, we're asking how far does the car move in total? And you can see that by the question marks that I've already have marked here for the displacements. And if we take the displacement part 1 and the displacement part 2, we can add them together and find what the total displacement is. And we can only do that if we find them for individual ones. Remember, our equations only work so long as acceleration doesn't change, which means we wouldn't be able to find the total displacement without splitting it up. So let's take a look at the values that we are given in this problem. So first thing that we're told is that during part 1 we are at rest. So at rest, as we should know, always means that we have a 0 for a speed, and this is at the beginning of part 1, so that would be the initial velocity of part 1. And then we have a rate of 2 meters per second squared. That's the first acceleration, so of course it goes right in there as a 2. We have a 10 seconds, which is how long the first one lasts for. So that means we throw it in as a time for part 1 only, not part 2. Other values that are pointed out to us is we have our -1 meter per second squared, of course, which goes in as our second acceleration, and we are coming to a stop, and stop always means that we have a 0 speed, and this is coming to a stop, which means that we have it as a final velocity. Now, the fact that these are both 0 is just a coincidence. Do not take that to mean that they will always be 0 to each other. It's just happened that way because of the fact that we started off not moving, and in this problem we ended up not moving. We could have just as easily asked about, well, when are we moving at only 2 meters per second? Or if we started at 2 meters per second, we could have easily thrown either of those in as a 2 instead, but not necessarily that they would have to be both. So here we go on to solving this out. Okay, so what are we looking for? So the first one we can solve for directly. Part 1's displacement. Well, we choose our equation. This equation makes sense because if we look back at our data table here, we knew everything that was in it, right? We knew that our acceleration was 2, we knew our time was 10, we knew our initial velocity was 0, and we wanted to solve for displacement. The only equation that has that is, of course, this delta x equals vi t plus 1/2 at squared. We don't even have to rearrange it in this case. So all we do, plug in our values, and we end up with a total of 100 meters. So, well, how do we solve for the next part? I mean, if we look at this, we had 3 values on part 1 side. It's very easy to see that we could just solve for delta x over here. But if we look at part 2 side, there's no third value, which creates a problem for us. And that's because we need 3 values in order to solve anything. Even our average velocity equals displacement over time. Average velocity really is knowing the initial velocity, the final velocity, and the acceleration all in one. So that doesn't really help us. We need a third value. So which could we use? We could go for part 2's initial velocity, or we could go for part 2's time. Well, which could we actually solve for? Well, here's the nice thing about it. Part 2's initial velocity is actually related to part 1's final velocity, and that's because those two are actually the same thing. If you think about it, if we are talking about, say, a ball being thrown up into the air, as you accelerate the ball upwards, you give it speed, and then the ball releases from your hand, and that speed isn't gone. It hasn't gone anywhere. When you release it from your hand, it goes flying up into the air, even though the acceleration is now switched over to the acceleration of gravity downwards, which would slow it down and make it come to a stop, which is why it has a maximum height. But those velocities, the velocity that you ended with in part 1, which would be raising your hand, and the velocity that starts with when it flies out of your hand, those are actually the same value. So that means that we can actually find this initial velocity of part 2 by finding the final velocity of part 1. So we have to go solve for the final velocity of part 1. And we can do that fairly easily. We got 3 values. We got the initial velocity, the acceleration, and the time. So we can just use this wonderful equation here. And this wonderful equation, when we plug stuff in, again, we didn't have to even rearrange for anything. It's very nice in that regard. We can find out that the final velocity is actually 20 meters per second. Wonderful. So what do we do with that? Well, now that we know that part 2's initial velocity must be 20 meters per second, which means that we can now solve for part 2's displacement. Because now we know that this is 20, we know that this is 0, and we know that this is -1. We can use our fun equation that we keep using in all of these videos. And VF squared equals VI squared plus 2A delta X. Rearrange that one, which you should be used to by this point. And then we solve this out, plug in the values as they're supposed to be, 0, 20, 2, and -1. And what we can see here is when we solve this out, we get a value of our second displacement being 200 meters. Now we're not done here because, again, we haven't answered the question yet. So what is the total displacement? Well, we take displacement 1 and add to displacement 2, and we find that it is actually 300 meters. So we're all done. We found it out. This is how you run a part 2 problem. Okay? So I hope you learned something from this, and I will see you in class. Phi Guy signing out.